Hey everyone, thank you for joining today. This is the second part of the presentation that I've been giving on um, my paper submission, low latency timbre interpolation and morphing using autoencoding neural networks that I wrote with my collaborator Sam Keene. My name is JT Colonel. Again, as a quick introduction, I'm a PhD at Queen Mary University of London, and yeah, the slide presentation that's uploaded with AES is covering background information, giving a large overview of some of the literature in the field and some high level descriptions of the system architecture. But here I figured I'd go into a little bit more detail into the nitty gritty of the implementation and also show a demo of the software in action. In the interest of full disclosure, I tried getting the demo to play nice with OBS as a live performance, and I was getting a bunch of clicks and pops and skips, and it was just kind of not great. So what I will be doing instead is doing a voiceover of a video capture of a performance or the live demo of the software. I have some notes with me right here as well to make sure that I touch on what I want to. But yeah, let's get going. So you can see on my left a block diagram of the network that was presented in the paper. You have a standard like neural network autoencoder. You have your encoder and your decoder. And what you do is you only train one network, right? You train one encoder and one decoder, which is why those are both the same color in the diagram over there. And then you just copy the weights of the encoder between the two input streams of audio that you're going to be using here. So everything is done in Python 3.6. The neural network backend is handled by TensorFlow, although I'm using Keras on top of that for ease of use. And all of the audio backend is handled by PyAudio, which it gives Python bindings to port audio. So in order to have this software running on your machine, you need port audio, which Macs you can install using Homebrew, or in Linux Ubuntu, which is what I'm doing. That's just a like sudo apt-get type thing. And Python 3.6.6 I think is what I have here. But PyAudio gets pretty finicky if you're not using 3.6, so that's exactly why I used it. We've included code to train your network, which I'll show in a second. What else do I got here? Yeah, no, let's show that. So that is over. I'm gonna hide you, and that's over here. So yeah, we wanted to give something that's like pretty straightforward to use to train a network, but also something that allowed for less powerful computers and more powerful computers. So yeah, this is actually the second version of the software that's up on my GitHub. There's the Timbre Interp repository, and then there's something like a DNB repository, and all that does is it runs two parallel versions of the model you just saw at the same time. So you're allowed to interpolate and morph using 4 streams of audio at the same time. And it's something I've just kind of had a good amount of fun with, because once you have 2 streams of output audio that you sum together, you have a lot more options for performance. Because I'm a fan of the genre, but also to make sure I was keeping domains lined up, I called it like the drum and bass network. So that's what you can see here. You have the drum audio, which is just the first domain that you want to train on, and you have your bass audio, which is the second domain that you want to train on. Those you could just have as WAV files, MP3, whatever. I think FFmpeg handles that loading, so anything, you could probably put like a .obis or something, and it'll be able to handle it. I give users the option to have data sets of various sizes, so you can have a minimum of 1 minute of audio, 4 minutes, or 10 minutes, just depending on how much work they want to put into putting their own data set together. And then you have the option to train for 50 iterations, 150 iterations, or 300 iterations. So in the smallest case, you could train on 1 minute of audio for 50 iterations. If you want to train on 300 iterations, it's going to take 6 times as long. If you want to train, if you want to go from like 1 minute to 10 minutes, that'll take 10 times as long to train. But I thought it was important to give people the opportunity to decide how much like time and compute power they wanted to spend on this operation. So yeah, back to the network very quickly. Just want to make sure I covered everything I wanted to. Yeah, so the way that we have the software configured right now, the network's callback operates on 5 batches of 1024 points. So there's about like a 10 milliseconds worth of latency introduced into the system there. What else do I got here? Just audio function. Yes. So one note on the last part of this diagram right here, you see the Griffin-Lim algorithm is all the way on the right. That was actually something that was implemented by accident. The SciPy implementation of the ISTFT function actually has a built-in Griffin-Lim iteration. And so because we're using the SciPy ISTFT, you get a Griffin-Lim for free. Like, it's not something we had to implement. And using using a cross-faded sum of the 2 phases of the input audio streams tends to be a good enough initial approximation for that algorithm to like converge fast enough and to have like a cohesive phase as you sort of continue like using the tool. And yeah, the last note that I have here, although I'll start a like video demo of what this looks like, is for the model presented here. Our latent space is only 10 dimensions, and we input a 2049 point magnitude spectral frame. So that's a really, really tight compression, just like from an information perspective, and that's reflected in the output, right? You get these pretty degraded signals. It's something I personally like about the tool, but for future implementations, or if folks were interested, it's definitely possible to open up that latent dimension. The tool itself that we have here has like 10 faders that apply multiplicative gains to each of those latent dimensions. But if you have 100 latent dimensions, right, you could just tie each of those 10 faders to 10 dimensions so that you can still like control what's happening in your latent space while allowing a musician to like maintain a little bit more of that fidelity. But yeah, let's get along with this. So I'll put this down, and I have a copy over here so that I can monitor what's happening, and we'll do that, and we'll start playing on my end. So this is the D&B tool. You have the 2 parallel networks running, one on top and one on bottom. So those 10 faders on top control the network on the top, and the faders on the bottom control the audio on the bottom. I mistype in the model name here. So once that flips, we'll load the model and we'll start playing the audio. Those 2 checkboxes at the very bottom of the tool are bypasses, so that we can just listen to the original audio. But on the right side we have our flute, and on the left side we have our guitar. And I'll show what interpolating in the time domain looks like and what interpolating in the latent space looks like. So that's just your waveform interpolation. This network, the flute guitar model, yeah, there it is just trained on guitar scales and flute scales. But you can hear almost immediately that there is like degradation in the quality of the sound, but you're able to start using these neural network like timbre space interpolations in real time, like with that instantaneous feedback on a network that you trained yourself. And that's something I think is like really cool about the tool. And here I demonstrate how the morphing works. So instead of moving between one timbre and a reference timbre, you just input a timbre and then you morph it into like other portions of the latent space. And now I'll show these two scales that I have that were performed on a microKORG. So these are like synthesizer scales, and they're two samples of audio that are not a part of the training corpus whatsoever. So you get all these like really kooky results coming out of that. That's what they sound like bypassed. And I think I go back to morphing these. Oh, no, okay. So I also have another model that was trained on a microKORG data set. So we can load, it hangs, and then it's loaded. And the warping as well. And to go back to the flute and guitar example, this is what those input sounds sound like when they get put into this like microKORG timbre space. It's like a little bit frightening, but I'm into it. And finally, I load a model that's trained on Steve Roach's album Structures from Silence, or Structures of Silence. It's this like really great album. It's just like these really gentle like synth pads for about like 20 or 30 minutes. And you can, train a network on that sort of album to get sounds like you project things into a timbre space constructed by the sounds and the harmonic content of that album. Here I demonstrate something else from the paper, which is what happens when you interpolate between something with a constant envelope and something with a more like percussive envelope. And then finally, just a demonstration that the network and the software is like handling all these streams simultaneously, and you can, do your like weighted sum to like level adjust between the two streams. But yeah, so thank you all for tuning in, and have a great rest of your day.